So when you're trying to measure the frequency of a crystal in a system, you're going to have a problem, because when you stick your probe in the 10x configuration, you're gonna increase the load capacitance by about 15 picofarads, and that what it's going to do to the system is by increasing the load capacitance, the frequency generated is going to go down a little bit. So if you just want to make a rough measurement, you could use the of the two pins, it would be better to use the output pin, in this case the XC2 pin. But if you want to make a more precise measurement, it would be better if you make a little circuit with a high-speed comparator. In this case, I researched for comparators with the least input capacitance, and I found the max 9010, which has a very low input capacitance. Here it is, 0.8 picofarads. So using that circuit, that IC, that comparator, I've made a little PCB that you can see here. So what we have here is the comparator. It's in an SC70 package. Here's a series input resistance to the non-inverting input. The inverting input is with a capacitor to smooth out the signal, and here in this hole I am gonna connect a trimmer, the middle lead of a trimmer, to input a reference voltage, and these three capacitors are for filtering the power supply. And this one is ground, and this one is the output. So I'm gonna show you how does it looks like. It's like this. Here's the trimmer, here's the power supply, here's a little botch circuit, but then that's no problem. It's not going to be a commercial circuit, so I can live with that. And there it is. The camera can't focus very well, but that's it. And I added a little bit of solder mask here, just to make the parasitic capacitance even lower. So the total impedance of the circuit would be like this. We have an input resistance, it's called differential input resistance, I think, of about 250 kilo ohms, and an input capacitance of 0.8 picofarads. So in this case I'm going to be measuring a 16 MHz crystal with the 0.8 picofarad capacitance, and it's going to give me a 12.4 kilo ohm impedance here. So having these two values and my series resistor, we can have the total impedance of the circuit. So what I'm gonna do, well, first I wanna show you just a little bit. So that's it. I'm measuring a 16 MHz crystal of this small module. There it is, and we can see it right there. So here the oscilloscope has let's say a poor counter. It tells me that it's about it should be 16 megahertz, but it's about 3 kilohertz more than it should be. I can use now a nice counter. to measure the frequency, and a more precise measurement gives us 2.8 kilohertz more than what it should be. For this case, in this module, in this module with this IC that it's being used, the datasheet says that it has to be a maximum 60 parts per million crystal. So as you can see, it should be between these two values, and it's way off the value that it should be. Now I would like to show you what would be with this LCR meter. What's its input, how much it's the input capacitance. It's about 1.2 picofarads. Let's see if we can measure again, and yes, about 1.2 picofarads, and no, that's it, 1.2. And if I flip it, it's flipping it, it's about 1.5 picofarads. It's just a little difference. So that's it. You can make an adapter for your oscilloscope probe to measure crystals with a very, very low input impedance, so you don't alter so much the capacitance load of your crystal. So that's it.